The neuromuscular junction, the junction or space between the neuron and the muscle, and all the components in it. So here we have a neuron with some myelin, some Schwann cells wrapped around it. And here is the terminal and the terminal bulbs, the end bulbs. Now the neuron will generate an action potential, which will then propagate and send the signal to the muscle. So around here we have the muscle. The neuron and the muscle are not actually connected with each other. There's a gap between them, a very small gap. The neuron will pass on the action potential to the muscle by releasing chemicals called neurotransmitters. A neurotransmitter can be inhibitory or excitatory. We will focus on excitatory neurotransmitters. Let us zoom into one of these end bulbs to look at how a neuromuscular junction operates. So here we have an end bulb. This is a simplified diagram, by the way. And on the other side we have the muscle. Both are separated, again, by a very small gap. These channels here on the muscle are called the ligand-gated sodium channels. We just have to remember these names. And as the name suggests, it's for sodium ions. And on the neuron, we have the calcium voltage-gated channels, channels for calcium. It is important to know that some ions are found predominantly on the outside of these cells. In this case, there are higher concentrations of sodium and calcium on the outside with respect to the inside of the muscle and the neuron. Both these calcium and sodium ions, however, want to go inside these cells, but are blocked by these channels, including the calcium voltage-gated channels. Now normally, there are vesicles situated in the neuron end bulbs. They contain many neurotransmitters. For skeletal muscle contraction, the excitatory neurotransmitters is called acetylcholine. So these red dots are acetylcholine. At rest, the inside of the neuron is negative with respect to the outside. But when an action potential arrives at the end bulbs, it will change the inside to become more positive. So action potential arrives, inside turns positive. This change in charge will then open up the calcium voltage-gated channels, allowing calcium ions to come inside the neuron from outside. So calcium influx. Now this calcium going in makes the end bulbs even more positive, and so causes these vesicles containing acetylcholine to release its content out. These vesicles are releasing so here we got the vesicles releasing acetylcholine. Now these vesicles are releasing the acetylcholine into what's called the synaptic cleft, or in this case we can refer it to as a neuromuscular junction. Acetylcholine will then bind to the ligand-gated sodium channels on the muscle, which will cause the channels to open up. The open channels will cause an influx of sodium ions to go inside the muscle fibers. So from a higher concentration on the outside, sodium moves into the muscle. Sodium influx. The sodium inside will generate an action potential within the muscle fiber, which will essentially cause muscle contraction. I hope you got that. Now let's see what happens after contraction, shall we? So here again, we have the neuron, the end bulb, the voltage-gated calcium channels here, and here is the muscle with the ligand-gated sodium channels. So after contraction has finished, acetylcholine will detach off the ligand-gated sodium channels and move back into the synaptic cleft. Sodium will move back out via some other different transport mechanism. So here we got acetylcholine moving out and now is in the synaptic cleft. Now, a special enzyme called acetylcholinesterase will break down acetylcholine. So here we have acetylcholinesterase, an enzyme, and here is acetylcholine. Note the similarity in name. Acetylcholinesterase will break acetylcholine into two molecules, collectively known as choline, and acetate. So the enzyme does this to all the acetylcholine in the synaptic cleft. Choline can be recycled again and combined with acetyl-CoA to make new acetylcholine. And so this process keeps going. I hope you got that. Now let's look at everything again in a summary. So here we have the neurons and bulb, the calcium channels, these vesicles here, and here the muscle. We got the muscle with the sodium channels, the ligand-gated sodium channels. So the first thing that happens, so here muscle and the neuron. So again, let's recap. First thing that happens is an action potential reaches the end bulb. So action potential reaches it, and this causes calcium ions to come in because it opens up its channels. So calcium comes in. Calcium coming in causes these vesicles to release its content, acetylcholine, into the synaptic cleft. So here, the vesicles releases acetylcholine into the synaptic cleft. Next, what happens is that acetylcholine will then bind to the ligand-gated sodium channels on the muscle. So here we have the sodium channels again, and the acetylcholine will bind to these channels, which will then cause sodium ions on the outside to come into the muscle. Sodium comes in. The sodium coming in will then generate an action potential within the muscle, which will essentially cause muscle contraction. After contraction, acetylcholine will then unbind, and the sodium will move back out of the muscle, so move out into the extracellular fluid via some transport mechanism. So sodium moving out. Next, an enzyme called acetylcholinesterase will then break down acetylcholine, which is in the synaptic cleft. So here we have acetylcholinesterase. And here we have acetylcholine moving into acetylcholinesterase. Acetylcholinesterase will break down acetylcholine into two molecules known as acetate and choline. Choline can be recycled to make new acetylcholine. That was all. I hope you understood that, and I hope it made sense. Sorry for posting the videos late. More will be coming, hopefully. Please comment, like, and subscribe, perhaps. Thank you. Bye.